So I wanted to start with reviewing just briefly what we talked about last week. I didn't post the video on this because I figured I'll just kind of go over it really quickly, and this one will be in this video. But I wanted to talk about the reparameterizing a curve. So again, this is a little demo I set up, and I'll throw it on the site as well. But it's just showing kind of a way that we can look at how reparameterizing these curves work. So if you remember, this initial one is set up so that it is a circle of some diameter. We have it as a radius of 1 in this case, so it's a unit circle. These controls just set up like how far we can offset this projected line, and how big we want to make this circle. But for this, we want to leave it as radius 1. And then this bit of the definition here is sort of a complicated way to create this line. It's not the most straightforward way to create this line down here, but it's a way that ensures that the domains of those are the same. And for this purpose, we want to see that. So I could have just really created a line with the start and a direction, and given it a length. But I wanted to make sure that the domains were the same, so it's a little kind of convoluted how that works. Anyway, basically the point here is we have this parameter t, which you can sort of think of as if this were a path, like some path through like an object. Like let's say it was a projectile, like you were shooting a cannon or something. You can sort of think of t as a moment in time. And the curves are the sort of the path that it's going on. So it's kind of introductory physics, mechanics sort of things. But as I change the time, let's say we're moving through a certain x-y coordinate in space. Does that make sense as a way to kind of conceptualize that? It's not actually, you're not actually moving through distance in this case. You're moving, although you are moving distances, we're moving at some, I guess, percentage along that path. So if I set this parameter here to, let's say, 0.5, it actually won't be halfway along because this domain is in radians. It goes from 0 to 2 pi. So if I actually set it to be pi, it goes halfway along that curve. And this is just part of the reason because it's a circle that we're dealing with here. If this were a line, 0.5, if it was reparameterized, would work. But I'll show you that in a second. So anyway, we're moving along the circle and the line simultaneously. And we're just using this evaluate component, which, again, it's set here under curve analysis and evaluate curve, and you can see it has that letter T there. That's for the parameter that you're going to evaluate. And you give it some parameter, and in this case the curve is not reparameterized, and it will find that point on the curve. So this same demo then, if I, let's say, disable this exact same setup below, with the exception of this case, we're changing that evaluate component to reparameterize this curve. You can see this little icon here makes it is the difference. And so all I'm doing is right-clicking on that curve component and clicking on reparameterize. And what that's going to do is that's going to rewrite that curve in terms of, instead of, in this case, we were going from 0 to 2 pi for the circle. In this case, we're going from 0 to 1. So now when I move along that path, I can go in sort of percentages of 1, if you can think of it. So if I double click here and type in 0.5, that's going to get me halfway along both of those paths. 0.75 would be 3/4 of the way. I think you get that. The difference here is we haven't changed the length of the curve at all. We're only basically rewriting its domain, and this is actually sort of just a kind of diagram that shows that curve domain. Both of these are points along the curve. That curve has the same length in this case. It's just one is flattened out, and so you can evaluate some parameter along the curve using a. You can think of it like a percentage if the curve is reparameterized. So again, that was just a quick recap on reparameterizing curves. The same thing applies to surfaces, and we'll probably run into that when we do surfaces. All right, so let's look at parametric curves. So let's see what I've got here. So this is actually kind of a little. There'll be a slight history, but it'll be very anecdotal. And there's all kinds of stuff you can find on the internet about how this stuff used to be done and how it was how it's been translated into the kind of digital version of it. But these are draftsmen dealing with complex curves using what's called a spline, which is why we call them splines here. And you can see these little these big kind of weight things. Those are called ducts, and they're kind of heavy weighted things, and you can kind of pull them, and it affects the shape of that curve. And that's kind of how draftsmen used to kind of deal with these things. And that's another shot of them. They're almost like fishing anchors. They're kind of these big, heavy things that you can pull around, and they're meant to hold their place while you kind of trace your line.
This is like analog Rhino?
Yeah, this is analog Rhino, and so they actually. I won't get into all the history, and I'll probably mess some of it up. But basically, there's a kind of digital translation of this same approach, and we use things like curve weights and knots in a very similar way. And let's see if we can look at some of those. An example. So let me open up parametric curves. All right, and